Hi everyone. Today we'll be discussing about an important topic, that is Android boot process. We will see what are all the steps involved, why each and every step exists, and what is the role of each and every step, and how from each and every step the next step is getting transferred. So without further ado, we'll just get started. So the first step is in the Android boot process is the bootloader code execution. Bootloader code execution. The second step is bootloader. After that, we have the Linux kernel. Next, we have init. Next, we have Zygote, followed by system server. So these are all the steps which are involved in the Android boot process. So there is one more step without which the Android boot process is not complete. That is the launcher. So we will see how first step is started and how the subsequent steps are being called, or rather I would say executed, from 1 to 2 to 3, how these steps are executed. One point to note here is all these steps are executed in a chronological fashion, meaning it can't be like one is executing and parallelly 2, 3, 4 are being executed. No, it's not like that. It is in a chronological fashion. It's like a cascading process, like how from one something happens in this, because of that another process is called, and here something happens, the another process is called, something like this happens. So the first and the foremost thing is the bootloader code execution. Before that, I just want to point out few things. That is the first three steps which are there, that is these 1, 2 and 3. These are not Android specific, and these three, these four, the last four, are Android specific. What this means is basically we know that Android OS is based on Linux kernel, which means that Android doesn't have a kernel of its own, rather it uses Linux kernel. What that really means is um, the process management or memory management or stuff like that. It's not very much specific to Android. Yes, it is specific to Android, but I would say it's the same architecture which is there in any of your Linux desktops which you use. So this boot ROM code execution number one, or bootloader, and this Linux kernel, it's the same architecture you will find in your Linux machines which you have. Yes, a little bit of uh, customization is done, because for of course customization is being done because of different device peripherals. For example, the PCB which Android has and your uh, Linux machine has, Linux desktop has, is different. Your Android phone has a camera, it has a battery, it has a um, I don't know, few buttons, like that. So customization is being done in these three things, but other than that, it's the same uh, code which is there. It's the same architecture is being used here. So that's why we say these three are not really Android specific, whereas these four, that is starting from Init and Zygote system server and launcher, these you won't find anywhere else except for Android. So these are really specific, and this part, that is this Init, is really important. We will see this in detail, what are all the steps involved, and we will see the documentation as well. So the first and the foremost step is boot ROM code execution. So what this really means, so first thing I would like to point out is, everywhere else they say that bootloader is the first step, but no, it's not. It's the boot ROM code which is the first step in the boot up sequence. So this is the first step which is there. So see, why this is there? Because see, this is a very lightweight program which is there, which would in turn call bootloader. So when device boots up, when I would say, when the device is in a switched off condition, when nothing is, it's just dead, meaning it still has charge but it's not running, in a power off state. So you can't directly load very big programs. Rather, how you go is, load a small program which in turn calls another medium sized program, and like that you go in that order. So this bootroom code which is there, it's a really small piece of code which is there on uh, device's processor or the system on chip. This is the very first code that is executed when the device powers on. So it is there inside the processor, or the system on chip. This particular program or the code which is there, this is hard coded by the chip manufacturer. For example, it can be Qualcomm or MediaTek, etc. And this part, it cannot be modified. So that's really important thing which we have to note here. And its primary job is to initialize critical hardware, or I would say necessary hardware, and load the bootloader into the memory. So it loads bootloader, and before that it initializes necessary hardware. Why necessary? We will see. Because see, necessary hardware, see, it is the first step, so you can't go on and initialize different peripherals. For example, in a booting stage, you of course you don't need a camera. So what you really need is a PCB, a system on chip. You need access to memory. So these are the necessary hardware which is required. So that's what this boot ROM code does. It initializes all those things, and after that it loads the bootloader. So now that execution is shifted to bootloader, and one more thing I forgot to mention here was this this boot ROM code. Before loading the bootloader, it does an important thing, that is checking the authenticity of the bootloader using hash or any cryptographic methods. Why that is necessary is to ensure that the bootloader which it is loading is not being tampered with, and it is in fact authentic. Whatever the OEM has designed, it is that. So using some hash or any cryptographic methods, it will check the authenticity of the bootloader which it is loading. So once it's done, it will load the bootloader. So my bootloader is being loaded. So execution now transfers to bootloader. So this bootloader is responsible for initialization of hardware, and it loads Linux kernel. So this is typically hard coded into the SOC, like bootrom code. Even this is hard coded on SOC, and this bootloader sometimes comes in various stages. So it can be in Android. It depends on the OEM. Few OEMs have one various stages. So typically it comes in two stages. That is primary bootloader or the secondary bootloader. This people also refer as IPL, that is initial program load, and this as secondary program load. So yeah, uh, there is a reason why it's been split into two pieces, two parts. Like I told, you can't go and load very big programs or execute very big programs at the starting stage. So like how this bootrom code is a very lightweight and a small program which loads bootloader. It doesn't really load the whole of the bootloader, rather it loads primary bootloader. This point has to be noted. This primary bootloader, the ini the job of this primary bootloader is simple. It has to, even this has to initialize. So this is primary bootloader or IPL, initial program load. So this primary bootloader or the IPL, so its job is simple. It will initialize a few other device peripherals, and like it will detect, and it will set up external RAM. Yeah, once external RAM is set up, what it will do is it will copy. Uh, so it will this will copy my secondary bootloader into external RAM. Now this external RAM, what this does is a very big job. So now that transfer execution is being transferred to secondary bootloader, or secondary program load, we will see what this has to do. So this secondary bootloader or the secondary program load, what it does is it loads Android OS. How it does, we'll see in a minute. So it is at this point we will have access to various boot modes like fast boot and recovery, etc. Like that. This secondary bootloader does a very interesting job. That is, first it will locate uh, the Linux kernel where exactly it resides. It will first look for Linux kernel, and it will load Linux kernel. Before that, it will decompress the Linux kernel. I mean, this Linux kernel, it's a image, right? So it's compressed and kept in some location. So what it will do is first it will locate, it will decompress Linux kernel, and then it will execute the Linux kernel. So now that our Linux kernel is being loaded, the execution is being shifted to Linux kernel. So third phase in the Android boot sequence is Linux kernel. So the main uh, functionality of Linux kernel is to set up memory addresses. It will enable various device drivers, memory addresses. It will enable device drivers, and the most important thing which will do is it will mount the rootfs. So which will provide access to uh, system and user data. So from Android perspective, again, this is not, like I told it. It's not a. It's really not Android specific, but yes, it is worth noting that what are all the things it will do. So next is, inside this Linux kernel, we will have something known as init RAM fs. What it stands for is initial RAM file system. So it's just a temporary file system which is there. it's this temporary file system. It's actually loaded into memory during early stages of Android boot sequence. So there is actually a very specific reason why this is done. So it provides the necessary environment for the Linux kernel to mount the actual root file system, and it will start the system. So inside this init ram fs, we have something like I'll show you. We have a RAM disk image. It will, one second. So inside the Linux kernel, we have this init ramff, and it has a RAM disk. So inside this RAM disk only, we have this binary, that is init binary, which is there, which when executed, it executes the init.rc file. So so the main role of this init ram fs is it's loading Android specific init, that is init process which is there. This it contains init binary, that is this particular binary. And we have like, okay, so in Android we have various partitions, that is system partition, data, vendor, product, system ext, all those partitions. So this particular init ram ff, this will set up all those partitions. So once it finds this init executable, once executed, my init.rc which is there inside this will get executed. So once init.rc file is execute, I mean init binary is executed. This is dot bin. So when this is executed, which it will execute init.rc. So my boot sequence is transferred to the fourth stage, that is init. So this init is Android specific. Why, we will see. So there is documentation provided in cs.android.com. So this cs.android.com is basically code search. So entire Android code, you can, the AOSP code, you can look here. And so this is the documentation which they have given for init. So we will just go through few things. So Android init language consists of 5 broad classes of statements. So we have actions. We'll see each and everything in detail now. So there is actions, there are commands, services, options, and imports. So line starting with a hash. Okay, these are just comments. Fine. Okay. And next we have system etc init hardware and init.rc. So inside our if you go to ADB shell and go inside this particular location, that is system partition etc init hardware location, you can find this particular rc file, init.rc file over there. So this is the primary RC file and is loaded by the init executable. Init executable is nothing but init executable is nothing but this particular executable file which I have shown. So actions and services implicitly declare a new section. Okay, fine. What else do we have here? Okay, now we saw that there were five broad classes of statements. First is action commands. So we will look into each of them. So the first one is actions. So there is something uh, called as triggers in Android. So what necessarily happens is um, so triggers, right? We have something like boot, on boot, and these triggers are nothing but few events. So when we see this RC file, what we can find is it's just commands. If this thing happens, do this. If this thing happens, do this. So that trigger points which it is waiting for, like right, it's like a listener. So for example, we have a button click listener. So we have registered and we are just waiting inside that function on click. Whatever, we are just waiting for an event to happen and to execute all those statements. So like that, we have this on trigger. So once this trigger is triggered, I mean, it gets this trigger. So for that, there are these commands which are being executed. So actions are added to the queue and executed based on the order that the file contains name was passed. So like that we have. And in Android there are system properties. I'm sure you must be knowing system properties. So system properties are nothing but key value pair, like JSON data we have, right? In that we have key value pair. So uh, what it does is on on trigger. So for example, if some event it is waiting for, if that event is triggered, it has received that event, what it will do is it will set certain system properties. So that system properties which is being set, it will few other triggers will be there which will be waiting for that system property to be set, and some other commands will be set. We will see what are all how that happens. For now, you just remember, the point to be noted here is there are some triggers, uh, and once that trigger is received, some system properties or some commands are being executed. Here, some system property is being set. And if you see this, along with the triggers, some property, if it's waiting, it is reading some system property. So this is what I was speaking. Here, it is waiting for trigger as well as it is waiting for system property to turn true. So if you see this, right, on boot, this is trigger, and it's like and is and this property is nothing but system property. This first true which is there, it is not the value, it is the uh, name of the property. I don't know why they have given like this here. See here, they have mentioned here, first true is the system property, equal to true is they're just checking. It's like property ABC equal to true, like that they are checking. Once that this condition is met, they are executing this command, these commands which they have, that is system. Again, they are setting some other system property. So you look here, then when the boot trigger occurs, that is this, when the boot trigger occurs, and assuming the property true, that is this true they are meaning, assuming the property true equals true, then the order of commands executed will be, these are all the commands. Okay, so we'll just check, we'll just take these example. So for example, this is been mentioned. So I'm waiting for boot trigger to happen. Once that happens, what I'll do, I will set some property A to 1, again property B to 2. Here, what I'm waiting for is trigger boot, and also if trigger boot, I get that trigger and my system property. Okay, instead of this two, I'll say XYZ. Okay, I'm waiting for this boot event and my property XYZ is true. What I'll do, I'll set property C to 1, I'll set property D to 2. And again, here it's the same. So if you look this particular line, when boot trigger occurs, that is, I've got boot trigger. So these two, of course, this will get executed. This I have to wait. And assuming that property is true. Yes, now even this is true. This property which I was checking. So these two will execute. After that, again here, if this boot trigger which I was waiting, so these two will also execute. So that is what I have mentioned here. Then when the boot trigger occurs and assuming the property true is true, then the order of commands would be A, B, these all system properties A, B, C, D, E, F will be set to the following values. And they have mentioned one more thing. If in case if the property true wasn't true, meaning this condition is not met, then these commands will not be executed. That is what they have mentioned here. If the property true wasn't true, when the boot was triggered, boot is nothing but event, then the order of commands will be the order of commands executed will be these two and these two. These will not be executed. Another thing to note down here is if the property, okay, for example, this, if you look, if you if you look at this particular scenario, right? There is an order which has to be maintained. First, my property has to be true. This has to become true, and then only I should get this boot event. Only then this will get executed. It's not like, okay, I for time t1, okay, I have received boot trigger. Okay, boot event is received, and t10 after, for example, 9 or 10 seconds, this property becomes true. Doesn't mean that I will execute this. No, first my property has to be true, and after that only event has to come. They have mentioned it here. If the property true becomes true, this becomes true after boot was triggered, nothing will be executed. The condition the condition boot and property true equal to true will be evaluated to false because boot trigger was a past event. So these are just an example which I'm giving. So next in the line is services. This is really important because it decides our uh, next step in our Android boot process. So um, services. So what I can do is, okay, example. Before that, okay, we'll just see what is the syntax. So service, the name of the service is a keyword, name of the service, path name is nothing but the, okay, so this service, for a service, for example, there are many services. There is LMKD, low memory killer daemon service. There is ADBD, that is Android debug bridge, ADB daemon, install D. Like this, there are various services which are there in Android OS. So how we mention is how we start the service is like this: service with the keyword name, and these various services which I've said, these are native written. So there'll be a executable file which is there in some location. So that path which is there, if you see in Linux, if you use few commands like cat, for that cat in your root directory, there'll be somewhere an executable for this cat which is for cat. there'll be some executable. So that path which is there, for example, my ADB daemon which is there, that path I'll give here. So ADB daemon will be started like this: service with a keyword ADBD, that is ADB daemon. Path name is the executable for my ADB daemon file, and arguments if we want to give any arguments. And options, we have options we will skip for now. One example where this services is used is best example is like this. For example, I can have a trigger like this, uh, on usb.config.state equal to ADB. Then what will happen is I will start my service ADB daemon with path. Of course, I'll give some path here like this. So what this really means is, uh, inside your developer options, you have an option that is turn on USB debugging. So that toggle, so that won't be turned on from the starting. We have to turn that. The user has to switch it on. So I've okay. For example, today morning I have switched on my mobile. My this boot sequence has been done. Okay, this particular thing is in my RC file, init.rc file. This condition is there in my RC file. Today at 5 o'clock, for example, I went to my developer options. I have switched on that USB debugging. Then my service ADB daemon will be active. Only then I'll be connected to ADB daemon. So it doesn't matter if that trigger comes right right when you switch on, or a few hours after you switch on, or few days after you switch on. So whenever in this RC file, whenever you get this event, then the subsequent commands which are there, which will be executed. In this case, I have turned on my USB debugging, meaning I have changed my USB config state to an ADB mode. That is why here I am starting my ADB daemon service. So this was all about services. And what do we have else is, okay, there is something called as restart. So uh, inside init.rc file, for example, I may have few services which will, due to few course of events, will crash. Okay, it is the responsibility of init to restart those services. And another point to be noted here is the service which is being started by init, none of a user doesn't have any access to stop those services. If even if the user stops those services, init is going to restart the service again. And if init restart that service, for example here, ADB daemon service I'm starting. Okay, for that it is just it's like a function call. It's like a function call ADB daemon service, start ADB daemon service. Okay, so it's like this: a service ADB daemon, path name is given. Inside that, if this service restarts somehow, there'll be bunch of other services which are there associated to this ADB daemon. If this restarts, I want to restart all those services, some this XYZ services which are there under ADB daemon, which are dependent or related to ADB daemon. I want you to restart all that, and init will make sure that none of the services which it starts is stopping. So that is on restart. And there is another, what else do we have here? Okay, this triggers we discussed, right? Triggers of an action specifies one or more conditions. When satisfied, executes the commands in the action. Using an AND operator, we can combine various triggers like that. So the system property I was mentioning. So this is how we check on property A equal to B. These are just few uh, syntax they have mentioned here. So, and they have this trigger sequence also. So early, they have this early init, and they have this they have early init, they have init, charger, late init. This charger is nothing but uh, if your device is in switched off state and then you plug your charger, it doesn't your device doesn't boot up. It just goes to uh, it shows an charging animation. It doesn't boot up, but it will go to a charging animation. That is why this particular mode is for. And we have this ro dot boot mode. This boot mode equal to charger, so that's a boot mode. That animation which you see, that is this boot mode. And this late init triggered if ro dot boot mode is not equal to charger, meaning an actual boot boot up is happening. It's not just an animation, a charger is connected, an animation. No, uh, triggering a boot from charging mode. Okay. Okay, so I told, right, this charging mode is there. So we can do another thing. When there is this charging mode, we can long press the power button, and then this health daemon which is there, it will trigger a boot from the charging mode. That is what I've mentioned here. So here we have bunch of different commands which are used inside the RC init.rc file. This changing the file permissions, and then we have bunch of other commands. For example, enable service. We have insmod. So different Linux kernel modules we can insert. Here it's not a loadable kernel module. It's just a module which is loaded from the boot. So we can use this insmod to init uses this insmod to uh, install a particular Linux kernel. Uh, that is Linux kernel driver, that is device driver. So what else we have here? Okay, we have this imports. So import, we have to give the path. It's nothing but it's like a Java import. We use different, like in Java we use different classes using packages com dot android dot some xyz class. So here this RC file, there are different RC files. If you see, right, there are different RC files if you see here. So we have init.rc. Here we have init.usb.rc. Like this, there are different RC files. So what this init in this init.rc file, what it does is it will import this different RC files For example, this RC file, this usb.rc file, it has imported over here. So like that, those are for different imports. Go back. Okay. So that is imports, and then okay, services. We have talked about this start, restart, and stop is of course used for stop stopping a particular service. And after that, yeah, that's it. And also we talked about on restart, right? So what init does is, once if any service is restarting, some failure malfunction occurs, so it is, of course, like I told, it is the duty of init to restart that process. And if that particular service is if it restart, if it crashes 4 times in 4 minutes, uh, init is going to say that a system device critical failure has happened, and it has to do something for that. So yeah, so that is it. So if we'll just look through the init.rc files, like I told, there are this there are these triggers. So on early init, what should happen? It should write to various these uh, it should execute these commands. That is, write proc, some command is there. It should um, make directory some permission bits they have used. After that, here they are starting some daemon. After that, like this, inside this init.rc file, it's just commands which are that triggers and commands. We start services, stop services, like that it is there. And one such thing it does is, it will Yeah. So one such thing in this init.rc file, at some point, when due to some triggers and by setting some system properties, whatnot, okay, some at a point in this, while executing RC file, there is a point where this particular this particular thing happens. A zygote starts. So zygote is really Android specific. We'll see what this zygote does in a minute. So now that init is done, so at some point, so I'll just note write it here. At some point, it starts executing a zygote, and then what happens is, execution is being transferred to the zygote. So in zygote, there is a whole lot of things happening. So if you launch any application, an Android application, for example, an Android application is there like this. You are using some text views, some edit text you are using. So this text views and edit text which you are using is a class inside Android OS, that is in AOSP. So how have you this Zygote is the one which will allow you to use these classes. So what it does is it preloads these Java classes, and it preloads framework resources, and it initializes runtime, and there are few shared libraries which Zygote loads. And one point to be noted here is this init process which is there. This is the one of the first processes which is a Java that has Java uh, uh, code inside is the init. So this is the one which initializes Dalek virtual machine or Android runtime, depends on which Android version you're using, and it will preload all the Java classes. We will look from here. Yeah, so this is the first process that has a Dalvik VM. So Java classes are loaded, framework resources are being loaded. There are various preloaded shared libraries which are there. So one thing happen. So now that Zygote is being started, what it does is it uses a very unique thing. So, for example, it will be clear with this example. You have one application. You have one application. For example, let's say you have Flipkart and there is Amazon. Okay, so Flipkart uses few classes, few Android related classes. For example, like I told, it uses text views, edit text. These are actual classes inside Android OS. If you search in the cs.android.com, these are actually Java classes inside Android OS. So uh, text views and edit text, Flipkart uses these things. Okay, even Amazon uses these things. So Flipkart is a different process. For example, 197. Amazon is a different process, P198. So for some example, doesn't mean that in the same device, this class which is there, text view, this and edit text, it is common for both the processes. The memory pages which are there for both my processes, it even though Flipkart is a different process, Amazon is a different process, the memory pages which is there, it's the same for both the process. So that is the role of Zygote. So um, Zygote, what it does is it it forks itself into different classes. For example, Zygote, it has all the libraries, all the here we saw it, all the Java classes, all the resource frameworks, shared libraries, all those things. It will have. So this is Zygote. If any call comes to start any application, it will fork itself to create another process, and then again it will, if some other call comes, it will create another classes. But what really happens is these classes, shared libraries, the memory pages which are there, it's common for both the process. So that is how for each and every process a different set of resources, resource frameworks, Java classes are not there. All the processes use the same memory pages, that is the same Java class, the same libraries they use. So that is how Zygote really helps. So that bunch of all these things are not uh, duplicated. So once that is done, okay, we forgot to note this thing. So this in we'll come back to init once again. This init which is there, it will start different. We will come back to init once again. So I told that init which is there, it will it will start various daemons like install d and adb daemon and lmkd. So one such daemon was Zygote. So this Zygote, what it does is this Zygote, it will fork itself to create system server. So this Zygote, it will fork itself to create system server, and this system server is the first functional process that has a Java runtime inside it. And it is with this only that all the processes we interact with has started. So um, any application we see or any process we see, it's been started from this system server only. So now that execution has started, execution has shifted to Zygote to from Zygote, the execution has shifted to system server. We will see what all things happen in system server. So this system server, it is responsible for almost more than 90% of the system services that we use. So for example, we use various services like Wi-Fi manager or activity manager, power manager. So this particular thing which is there, system server, this is responsible for all of it. One such service is activity manager service, that is AMS. So this AMS, it is responsible for managing all the application states. So anything in Android you see is an activity and it has a life cycle. So it is managed by this activity manager service only. Yeah, so activity manager service. So this manages application states. If an application it goes to foreground, it comes to foreground, goes to background, it pauses, resumes, starts, or anything. This particular service, that is application manager service, is responsible for each and everything, handling the life cycle of all the applications which we interact with. This is the one which sends commands for each and every activity transition which occurs. And in this course of events, so there are few broadcasts which are fired. So one such is action main, that is action underscore main, and category home. So these broadcasts are fired. So it's nothing but this has an intent filter which is there. So any launcher which has registered which has this these intent filters can show up in the launcher application. So I'll show you how this thing happens. So what happens is, when in system server, uh, nothing but there are bunch of many classes are being instantiated. One such class is this uh, launcher class. So it will this broadcast is been sent. Any application that has this broadcast can become a launcher application. So uh, it happens like this. I am in my current application. My main activity is running. Okay, so a request has come to open an activity. So for example, there is launcher 3 which is there, that has registered to this broadcast, and once it receives this broadcast it will start an activity. So it could be something like in on receive, this is broadcast receiver. In on receive, it can have, once it receives it can start activity. So once this start activity command is given, what happens, like I told, each and every any activity which starts or process, it will come to activity manager service. So it start activity command is given, so it comes to activity manager service. Activity manager service, it will check if is the process already running or not. If it is running, yes. If it is not running, no. Then what it will do is, it will, if it is not running, it will come to Zygote. What Zygote will do, it will fork itself and create a new process. That is my launcher process. So once launcher process is created, a new application has been started. This is a new application. This is a new process slash application. So that is how my launcher comes in on the screen. And also one main thing is if that application is already running, it will just start the activity here. So this is how we come right from boot ROM code execution. So bunch of hardware is initialized in boot ROM code execution, and then my bootloader is loaded. After that, once bootloader, it initializes some more have few other device peripheral and hardware. After that, it looks for Linux kernel and it loads Linux kernel. What Linux kernel does is, it again it initializes few hardware, it loads few device drivers and memory management, all those things Linux takes care. And it Linux kernel also, at last, it starts the init process. So in init process, we have already seen in detail what happens, all those things. Various services are being started. One such service is this Zygote. So Zygote, it is the first application which is started, first process that has the Dalvik VM or R. So it will create various Java classes. It will load various framework resources and just be there for if any application is requesting to start any new activity. What this Zygote does is, it will just fork itself to become that application. So That is a role of Zygote. After that, we have the system server. So the system server is responsible for like everything, all the processes which we have. And after this, we have our activity manager service, which was not mentioned here, but yeah. So this activity manager service in turn launches our launcher. So this is how the flow of Android boot sequence is. So thank you all.